Now let's look at a special kind of matrix, the permutation matrix. A general matrix can be any rectangular array with arbitrary real entries. In contrast, a permutation matrix must be square. Its entries are only 0 or 1. Each row contains exactly 1, 1, and each column also contains exactly 1, 1. All other entries are 0. A permutation matrix is very similar to an identity matrix whose rows or columns have been exchanged. If we left multiplied a matrix by a permutation matrix, the rows of that matrix are reordered. In other words, it permutes the entries of a vector or the rows of a matrix. For example, consider a 3 by 3 matrix A. Suppose we left multiply A by a permutation matrix obtained from the identity matrix by swapping the first and second rows. The result is that the first and second rows of A are swapped, while the third row stay the same. Permutation matrices have some useful properties. For a general matrix, we usually find the inverse by elementary row operations, or Gaussian elimination. For a permutation matrix, the inverse is much simpler. Its inverse is just its transpose. Also, the product of two permutation matrices is again a permutation matrix. Such matrices appear often in computer science. For instance, they are used in diffusion layers in cryptography. They are also used in graph isomorphism to check whether two graphs have the same structure up to relabeling of vertices. Now we turn to the main task. We want to compute the number of proper square roots of the identity matrix IN for a given size n less than 21. To do this, we first need clear mathematical definitions. By definition, a permutation matrix B is called a square root of the identity matrix if B squared equals to IN. If B is not equals to the identity matrix itself, that is B not equal to IN, we call it a proper square root. Each proper square root corresponds to a permutation. This naturally leads to the notion of an involution. An involution is a permutation sigma such that sigma square equals to ID, where ID is the identity permutation. Applying an involution twice sends every element back to its original position. To find proper square roots of the identity matrix, I need permutation matrices B with B squares equals to IN and B not equals to IN. We can describe a permutation matrix by how it rearranges the rows of the identity matrix. For instance, we may write the identity as 1, 2, 3, meaning rows 1, 2, and 3 stay in place. A permutation like 2, 1, 3 means that rows 1 and 2 are swapped, while row 3 remains fixed. When such a permutation matrix multiply another matrix, the result is that the corresponding rows or columns are swapped in that matrix. If we swap two rows of the identity matrix to obtain a permutation matrix, and then perform the same swap again, we return to the identity matrix. So in this case, multiplying the permutation matrix by itself gives back the identity. This satisfies the condition B squares equals to IN. There can be many such swaps. For example, in a 5 by 5 identity matrix, we can swap rows 1 and 4, and at the same time swap rows 3 and 5. This also gives a permutation matrix obtained by performing two independent rows swap. However, not every permutation matrix have this property. For example, the square of the permutation 3, 1, 2 is 2, 3, 1. This result is not the identity permutation, so B square is not equal to IN in this case. So we ask, under what condition does a permutation matrix square to the identity? From the counterexample, and from the simple row swap case, we observe a key condition. Any pair of rows that are swapped cannot take part in any other swap. Otherwise, the original other will not be restored after applying the permutation twice. With this condition in mind, I consider higher dimensions. I list all cases for 4x4 and 5x5 matrices and try to observe patterns. Taking the 5x5 case as an example, my first idea was to choose one pair of rows to swap, and then perform swaps on the remaining rows. I noticed that the operation on the remaining rows behave like the 3x3 case, so I denoted the number of proper square roots in the 3x3 case by A3. In general, I write An for the number of proper square roots of the identity matrix of size n. At first, I tried to choose combinations to count. For the 5x5 case, I used 5 choose 2 to choose a pair of rows to swap. Then I applied a similar step to remaining rows. However, this approach produces many duplicate cases. The reason is that the second step also chooses pairs of rows, which overlaps with the first choice. To set up a better recursion, I changed the first step. Instead of choosing a pair directly, I first pick one element. I consider two possibilities for this element. This element does not take part in any swap and remains fixed. Then the remaining n-1 elements form n-1 multiply n-1 problem, so they contribute n-1 possibilities. This element is paired with another element in a swap. There are n-1 possible choices for its partner. Once this pair is fixed, the remaining n-2 elements form n-2 multiply n-2 problem. So for each choice of partner, we obtain n-2 possibilities together. This case contributes n-1 n-2. These methods avoid both duplicates and missing cases. As a result, we obtain the recursion formula an equals to an-1 plus n-1 multiply an-2. After that, first I describe the input, output, and key definitions. The program takes a single integer n as input. This integer is the size of the matrix. I use a try except block to handle invalid inputs, so the program does not stop when the user enters a non-numeric value. I also add a separate check to make sure that n is between 1 and 21, as required in the assignment. Inside the algorithm, I introduce two variables, a0 and a1. They are not random. They store the current state of the sequence. More precisely, they represent an-2 and an-1 in mathematical formulas. For the output, the program prints the number of proper square roots for the given n. It also prints a formatted list of the values for k from 1 to 20. I use this list to check how the sequence grows and to support the discussion in the report. Next, I describe the main functions. The main computation is in the function evolution count n. I compute the recurrence step by step in a for loop. The loop starts from the base cases, where the count is 1. In each step, it computes the next term ak using the rule. The new term equals the previous term plus k minus 1 times the term before that. After that, it updates a0 and a1 to move the next position in the sequence. The second function, it calls evolution count n and the minus 1 from the result. This step is important because the counting formula includes all evolutions. The assignment, however, only asks for proper square roots, so we must remove the identity matrix from the count.